Okay, so hello everyone. Welcome to the week 12 of the problem solving session for the discrete math course. So, what we'll do today is some advanced topics on counting. So, we will see what is a chromatic polynomial. Um, then we will also look at some results from group theory and how to use these polynomials for counting. So yeah, that's the okay, so that's the agenda for today. So let's start by defining what a coloring of a graph is. So we have seen this at some point in the course, but yeah, let's recall some concepts. Let's recall that we define proper coloring as follows. So you're given a graph and um, yeah, and your job is to color the vertices in such a way that no two adjacent ones get the same color. So for example, if I color this guy with red, then I cannot color and then I cannot color this one with yellow because if I color this with yellow, then I cannot color this one with yellow again, because these two are adjacent and I don't want neighbors to get the same color. So what I do is I pick a different color and color it with this. Now I try to color this vertex. Notice that this is adjacent to yellow as well as green, so this has to get a color which is different from both yellow and green. So what I do is I pick the next color and I color it with that. Now I look at this vertex. It cannot get a color of blue, but it can surely get a color of anything other than blue. So I'll try to reuse the colors because I want to color this with as minimum colors as possible. So I'll do this yellow, and then I look at this vertex, and again it can't get a color of blue or yellow, so I'll color it with green. So I use three colors. So the chromatic number for this graph is at least three, and you know that you can definitely color it. If you can color it with three, then you can always color it with 4, 5 and so on colors. But if I want to find the minimum number of colors with which I can do a proper coloring, then that turns out to be 3 for this graph. So by proper coloring we mean that for all EI EJ such that EI intersection EJ is not equal to phi, the color that you are giving to the okay, maybe I'll sorry yeah, for all vertices Vi Vj such that Vi Vj is an edge, the color of Vi should not be equal to the color of Vj. Okay, and yeah, so that's how we define the proper coloring. Now the question that we're asking is, let's say instead of three colors, if I had if I had an inventory of some lambda many colors, so instead of three I have a lot of colors and so on, and there are lambda many of them, then I want to know in how many ways can you color this graph. So that is what is given by the chromatic polynomial. So the chromatic polynomial gives you the number of ways of proper coloring of a graph G using lambda colors. Okay, so we will see this with some illustrative examples. So let's look at the first one. So let's say you're given this graph here. This kind of a graph is what is called a star graph, where you have a vertex in the center and then you have edges like that going outside. So the question that we're asking is, if you have lambda colors at your disposal, then in how many ways can you properly color this graph? Okay, So let's let's try to solve this. So this is what the graph looks like, and okay. And now what you do is, let's say I have lambda colors here, and I want to color this guy. So I can color it in lambda many ways. So there are lambda choices for this. So there are lambda choices for the first vertex. And now let's say I want to color one of its neighbors. So let's say I want to color this guy, and I cannot choose the color that is assigned here. Other than that, I can choose any of the other lambda colors. So that means I have exactly lambda minus 1 choices for this. Similarly, I have lambda minus 1 choices for this, lambda minus 1 for this, and so on. So that means the total number of ways in which I can do this is lambda for the center vertex and lambda minus 1 for the other 4. And that gives you lambda times lambda minus 1 to the 4 as your chromatic polynomial for the graph that is given to you. And now what you do is, if I tell you, now lambda is a variable here, so now if I tell you that, okay, look, I only have like 3 colors at my disposal, then what you do is you can quickly substitute lambda to be 3 and evaluate the value of the polynomial at 3, the chromatic polynomial, and this will give you 3 times 2 to the 4, and that is 3 into 16, which is 48. Now the interesting thing is, notice that the chromatic number of this graph, which is the minimum number of colors you need to properly color it, is 2 in this case, because I can choose a different color and this is a proper coloring. So if you give me 2 colors, I'll be able to color it without violating any constraints of the proper coloring. But I can't do, for example, with one color, because if this is colored yellow, this cannot be colored yellow. So 2 is the bare minimum colors that are needed. So what happens is, if you substitute here lambda is equal to 2, then the value of your polynomial is 2 into 1 to the 4, which is 2, and that is because there are only 2 ways to color this. One is that you do this, or the other is that you swap the colors. That is you color this guy with green and then you color the other guys with yellow. So these are the only 2 colorings that are possible if you give me 2 colorings, and that matches with the number p of 2 that you have. But let's see what happens, the interesting thing that happens when when lambda is equal to 1. So if lambda is 1, then we know that there cannot be a proper coloring there cannot be a coloring with a single color that is still a proper coloring. So let's see what the polynomial tells us. So I substitute p of 1 here, and that gives you 1 into 1 minus 1 to the 4, which is 0, and that exactly matches with the fact that you cannot do a proper coloring if you just have one color. So the chromatic polynomial in that sense captures all the corner cases, and it's just a nice way of counting the number of proper colorings by just substituting the value of lambda. So yeah, so that's the warm-up example. So let's look at let's look at another graph. So in this case, it so happened that this was a very easy case where you could like sort of start with the coloring and then notice that, oh look, the other ones only have lambda minus 1 choices. But that may not happen always, because the underlying graph could be very, very complicated. So let's look at an example. So consider this one, for instance. Now if you try to, okay, so in this question you are asked to find the chromatic polynomial of the graph that is given to you. And so what you do is, if you try to trivially do this, it may not always nicely work out, because okay, let's try doing that. So let's say you color this guy with yellow. Okay, maybe I'll not do that. Okay, let's say you have lambda choices for this vertex t. And then you look at this vertex C, and then you have lambda minus 1 choices for this. And then you look at this vertex E here, and then you have lambda minus 1 choices for this. But then if you look at this vertex B, it is not very straightforward that it should have lambda minus 2 choices, because that clearly that depends on what color this A gets, and whether the color of A and the color of C is the same or not. Because if A and C are the same, then B should have lambda minus 2 choices, because it can't be the same as the color of D, it can't be the same as the color of A and C. But if A and C are of distinct color, then B has lambda minus 3 choices. So there are some cases that come up here. So this is something that we saw in the lectures, and this is where so one thing you could always do is you can always deal with the cases separately, and then sum up the answers for those cases. But the nice formula that we saw in the lectures is that if you want to find the chromatic number of the graph, then you look at an edge in the graph, and what you do is you delete that edge from the graph and find the chromatic number for the resultant graph. So for what I mean by that is, if I give you a graph like this, and this is an edge E, then by deletion I just mean that this particular edge is deleted and everything else remains the same. So yeah, so that's what we mean by G minus E. And then what you do is you separately contract the edge of the graph and try to find the chromatic number for the same. So what do I mean by contraction? Let's say this is your graph again, and I'm contracting this edge. Then what that means is I'm sort of clubbing these two together. So these two will be joined together, and what you get after G dot E is a graph that looks like this, where this vertex is like sort of you push together these two vertices and club them into a single vertex. And this is exactly capturing the notion that we had. So the notion that we had, that the difficulty that we had in the beginning was, let's say this is an edge, and like we said here, the color of B depends on whether the color of A and C are the same or not. So if they are distinct, if they're distinct, then you can just think of them as being clubbed together, and if they're not the same, then you can think of it as being deleted. So I'll not expand on this further, but this is something that we saw in the lecture. So what you need to remember for solving the example is this formula, which will be very handy, as you will see now. So let's maybe I'll start by picking this edge dB. So I'll maybe get a new page. So this is the graph that I have. And I'm talking about this edge here. Okay, so what I'll do is I'll split this into two cases. One case is where I'll delete the edge, the other case is when I'll contract the edge. So let's look at what the graph looks like. So in case of deletion, it's just that you're removing this edge from the graph. So what does the graph look like? You have E, A, B, C, D, and if you look at G dot E, that is E, A, B, C, and this becomes a multi-edge, and E to D is an edge. So this is what it will look like. So basically what happened is, once you identified D with B, this edge that was incident from E to D will now be incident from E to B. So that's why we have this. And this other edge that was incident from C to D will now be incident back to B again, because B and D are essentially the same vertices now. So this is nothing but D. So let's try to solve. So the nice thing that has happened here is, in order to solve for this big graph here, I'll first find the polynomial for this graph, I'll find the polynomial for this graph separately, and then I'll just add them together, and that will give me the chromatic polynomial for the bigger graph. And the nice thing is, you can just keep on repeating this process again. So let's say I want to find out the chromatic number for this, the chromatic polynomial for this, then I can just again identify an edge, merge it together, and then keep on finding and adding up the answers. But in this case, it so happens that the answer is not very difficult. So let's try to color this intuitively. So let's say I can color this, let's say I start by coloring this vertex, then I have lambda choices with me right now. And for this vertex, since it's adjacent to B, I can only color it using lambda minus 1 vertices, because the color can't be the same as that of B. Similarly, if you look at A is adjacent to this B, therefore there are only lambda minus 1 choices for it. And now if you look at E is adjacent to A as well as B, therefore the color of it has to be different from what you have colored for B as well as what is colored for A. So two choices are gone out of lambda, therefore you have lambda minus 2 choices for this. Okay, so what is the total number of ways in which you can do it? You can color B with lambda colors, then you can color C with lambda minus 1 colors, and A with lambda minus 1 colors again, and E with lambda minus 2 colors. So the chromatic polynomial for this is lambda minus 1 whole square times lambda minus 2. And so that's the answer for your chromatic number for G dot E. Now let's try to solve for the chromatic number of this G minus E graph. And again, what I can do is, I can appeal to the same idea. This time let me try with contracting deleting and contracting this edge. So that gives you two graphs now. So that gives you G prime minus E and G prime dot E. And what does that look like? So for the deletion case, you are just deleting that edge. So this is what it will look like: E, A, B, C, D. And for the contraction case, it will look like E, D, C, B, which is same as A. And you will have this edge which was going to A earlier, and since it's identified with B, you can just add that edge directly to B. Okay, so let's try to solve for them, and then finally we will add this together. So in this case, again, this is an easy case, because what I'll do is, for the first vertex A, I'll color it with lambda colors. For the second vertex E, I have lambda minus 1 choices, because I have to choose something that is different from the color of A. Then for D, again I have lambda minus 1 choices, C I have lambda minus 1 choices, and B again I have lambda minus 1 choices. So the chromatic number of G prime minus E is lambda times lambda minus 1 to the 4. Now let me try to solve this. Let's try to solve this for the second graph, the resultant graph that I have. And yeah, maybe I'll do the same thing again. So I'll this time I'll choose this edge, and I'll contract it, so, and delete it. So now G double prime minus E and G double prime dot E. So what does this look like? So this is simply G prime minus E is simply a path of length 4, and what is G double prime dot contraction E? It is E, D, C, and that's it. That's just a cycle of length 3. So if I want to color this now, again it's the same idea as the path of as we did earlier. For the first vertex, you have lambda choices. For the second vertex, you have lambda minus 1, then again you have lambda minus 1, and again you have lambda minus 1 choices. So the chromatic number of G double prime minus E is lambda times lambda minus 1 to the 3. And if I want to find out the chromatic number for this, then I'll do the same thing again. So for the first guy, I can color it with lambda choices. For the second one, I can color it with lambda minus 1 because it's already adjacent to D. And for the vertex C, it's adjacent to D as well as C, which are both distinctly colored. So two choices are gone out of lambda, and you're left with lambda minus 2. So the answer for this is C double prime of G dot E is lambda times lambda minus 1 times lambda minus 2. So now what we will do is we will take all these answers and then we will add them together. So this is one answer, this is the other answer, this is the third answer, and this is your fourth answer. And what we will do is we will add them all together. So the answer is going to be finally yeah, so the answer is going to be lambda times lambda minus 1 to the 4 plus lambda times lambda minus 1 cube plus lambda times lambda minus 1 lambda minus 2 plus lambda times lambda minus 1 square lambda minus 2. So if you try to expand this, what you finally get is lambda minus 1 square cube times lambda minus 1 plus 1. So this is lambda minus 1 plus 1 plus lambda minus 1 lambda minus 2 times lambda minus 1 plus 1. So this is nothing but lambda square lambda minus 1 cube plus lambda square lambda minus 1 lambda minus 2, and that is nothing but lambda square lambda minus 1 lambda minus 2 plus lambda square minus 2 lambda plus 1, and this is nothing but lambda square minus 3 lambda minus 1. Yeah, so that's finally yeah, if you simply if you try to simplify this, then this is what you end up getting. And so the chromatic polynomial for the graph that is given is this. Okay, so now again, if you just tell me what is the value of lambda, that is how many colors do you have, and then we can plug this into the formula, into the polynomial, and just get the number of colorings, the number of proper colorings that you can have, yeah, using this. Okay, so okay, so next what we will do is we will look at this concept called partitions of a number. So what I mean by that is in how many ways can a partition find. So let's maybe first understand in how many ways can you partition 3, for example. So if I want to partition 3, then I can write it as 3, or I can write it as 2 plus 1, or I can write it as 1 plus 1 plus 1. Notice that in this case 2 plus 1 and 1 plus 2, these are not different, it's the same thing, the order does not matter. So there are only 3 ways. So there are only 3 ways in which you can partition 3. So the number of partitions that 3 has here is 3. So P of 3 is 3. So let's understand the number of partitions that you can have for 5. So one is that you just have a 5. You could have 4 plus 1. You could have 3 plus 2. Or you could have 3 plus 1 plus 1. Then you can have 2 plus 2 plus 1. or you could have 2 plus 1 plus 1 plus 1, or you could have 1 plus 1 plus 1 plus 1 plus 1. So the total number of partitions that you have here is 1, 2, 3, 4, 5, 6, 7. So the number of partitions that you can have for 5 turns out to be 7. So the number of partitions, so the answer for the first part is 7. And now the question we are asking is how many of these are distinct partitions and how many of these are odd partitions. So what do I mean by distinct partitions? So what are distinct partitions? Okay, so what you do is you look at all these partitions and look at the numbers that are involved in them. So in this case there is 5 which is not repeated, so 5 is a distinct partition. Then let's look at 4 plus 1. This is a distinct partition because none of the numbers is repeated. Again 3 plus 2 is a distinct partition because 3 and 2 are distinct. But now let's take a look at 3 plus 1 plus 1. Here the number 1 is repeated twice. That's why it's not a distinct partition. And let's look at the number, the second one. Here the number 2 is repeated twice, and therefore this is also not a distinct partition. Here 1 is repeated and here again 1 is repeated. So there are only 3 distinct partitions here. So the number of distinct partitions, this is denoted by PD of 5. D stands for distinct. Here is 3. Now let's take a look at what are the odd partitions. Okay, so let's say I'm looking at each of them again, and I want the numbers that are participating in the partition to be odd. So 5 is odd, so 5 is a distinct partition. Here 4 is not odd in the second one, so this is not a distinct partition. This is not an odd partition. Here 3 is odd but 2 is not odd, so this is again not an odd partition. But here 3, 1, 1 are both are all odd, so this is an odd partition. This is not an odd partition because of 2, this is not, but this is again. So you have 3, I'll denote it by P0, PO of 5, and it also turns out to be 3. Now what you can do is you can ask if is this a coincidence that the PD of 5 and PO of 5 they both match. Similarly, if you try to do it for 3, for example, if you try to identify the odd partitions, then odd partitions are 3 and 1 plus 1 plus 1. So there are PO of 3 is 2. If you try to find the distinct partitions, then 3 is a distinct partition, 2 plus 1 is a distinct partition because none of the numbers is repeated, but 1 plus 1 plus 1 is not. So the number of distinct partitions is 2 again. So in this case also PO of n and PD of n, they both match. So in general it can be shown that for any number n, PO of n is equal to PD of n. That is, the total number of distinct partitions is equal to the total number of odd partitions. And this is something that we saw how to prove using polynomials and generating functions. So I'll not get into the proof of that right now, but it's just something nice to recall, and it's a very nice theorem to observe and prove. So that was just to recall the partitions, the odd partitions and the distinct partitions. So yeah, so now what we'll do is we want to find out, you've given this number 42 and you want to find out what are the total number of distinct partitions of 42 in terms of coefficient of a polynomial. So we want to view this in terms of polynomial, so that like we saw in case of chromatic polynomial earlier, again you can just plug and place the values and it gives you a general solution. So similarly I want to view this in terms of polynomial. So okay, so what we said last time in the course was the PD of x is given by 1 plus x, 1 plus x square, 1 plus x cube, and so on, 1 plus x to the 42. Now why is that? Simple intuition behind that is that if from the first partition, if I choose the number 1 from the first partition, then I then I do not want to choose it again. So that's the only way. I cannot have like this 1 plus 1 plus 1 and so on. I don't want to allow these repetitions, and that's why I only have 1 plus x. One is that I did not choose 1 at all, and next tells you that I chose it once. Similarly, the one here tells you that I did not choose the 2 at all, and x square tells you that I chose it exactly once. Similarly, 3 I did not choose at all, or I chose it exactly once, and so on. You have the choices till 42. So for example, if I just pick 1 1 1 and so on, and finally I pick 42 from the last one, then what do I get? If I multiply all these terms, I get x to the 42. And what does this correspond to? This corresponds to one partition wherein I don't wherein I only choose 42, and from the other houses 41 40 and so on all the way up to 1, I do not choose them at all. So this is one valid partition that we saw. Similarly, if I if I choose 2 and 1 plus x to the 40 from here, and everything else is 1, then again I get x square times x to the 42 times 1 1 1 from all the other houses, and 40, and that gives you x to the 42. So that is another way of partitioning, which is from 40 I choose 1, from 2 I choose 1, I choose 40 2, and everything else is 0. So that adds up to 42. So that shows you that there is a bijection between a term that you obtain from a product here and the partition that you have. Therefore, the total number of distinct partitions of n is equal to the coefficient of x to the n in the expansion in the polynomial 1 plus x, 1 plus x square, and so on all the way up to 1 plus x to the n. And that's the solution. So in this case, what you're looking for is the coefficient of x to the 42 in the expansion of the following polynomial. Okay, so so that is a nice that is one nice way to use polynomials to find your answers counting problems. And similarly, we saw a polynomial for finding the total number of partitions. We also saw a polynomial for finding the odd number of partitions. So that's something nice and interesting to look into, but we will not cover that today. So I'll move on to the next question. So okay, so before we get there, maybe it might be a good idea to recall what a group is, and then we can dive into solving the problems. Okay, so what we'll do is let's maybe recall what groups are. Okay, so groups is an algebraic structure which consists of a set which is nothing but a collection of elements in no particular order, and it is associated with an operation. So the operation could be anything. I'm not defining it for now, but the operation takes two elements from the set S and applies it. So A, for all A, B in S, you can define this operation. This is the operator. So I'll call this operator, and this is the set S. And the set need not be finite, the set could be infinite, does not matter. Okay, and now so you can always choose a set like that. So maybe I just have a b c d e all the way up to z, and then I define some operation, um, which is maybe take a union of them, or maybe just concatenate them. Okay, concatenate the two strings and so on. So I can always define it like that. This is the concatenation operation. But is it true that any set and any operator can be called as group? No. So it so happens that if the set that you have in hand and the operation that you have in hand, if they satisfy certain nice properties, then we say it's a group, and if otherwise it is not a group. And why we're interested in these properties is that these are very useful to solve problems right and left, and this come in a lot of places in computer science. So the application of that may not be very easy to motivate at the moment, but let's try to define what a group is. So you say it is a group if it satisfies four properties, and the properties that we want, first is what is called the closure property. That is, if I say if I take any two elements for all a b in the set S, if I do this operation a star b, then the resultant element should also be in the set S. Now what do I mean? The second property that you have is associativity property. And what do I mean by that? So if you look at any three elements in the set S, then a star b star c is same as a star b star c. That is, it does not matter whether I did an operation of ab first and then with c, or whether I did bc first and then with a, the result should be the same. And the third one is what is called the identity. And what that means is, there is an element E in the set S such that for all A in the set S, A dot E, A star E is same as E. Okay, and the fourth one is what is called inverse. And what we mean by that is, for every element in the set S, so this E that we have, this is called the identity, by the way, identity element of the group. And what do I mean by inverse? Inverse says that if you look at any element in the set S, there has to be another element a prime in the set, such that if I do an operation of a with a prime, then I get back the identity element. So so just by looking at this, it's not very clear why these properties are interesting to us, but hopefully as we'll look at the examples, hopefully things will be clear. So just a point to note here is, why am I interested in only these four properties, and why not like just say, what if I don't have this inverse, or what if I don't have this identity, and so on. So it turns out those algebraic structures are also very well studied, and they go by different names. So some which do not have the algebraic structures that satisfy closure, associativity, identity, but not inverse, these are called monoid. And similarly, if you just have these two properties, then there's a different group corresponding to that. If you add in one more property, if you add the property of commutativity, that is, if I have a star b is equal to b star a for all a b in S, then you say that the property is commutative, and such a group which satisfies all the four properties goes by the name abelian group. And this group is also very well studied, and maybe if we come across such an example, then we will definitely point that out. And so far all you need to remember is these are the four properties that define your group. Okay, so let's see this with examples. So okay, so let's look at the first example, which is z plus. Z means z is the set of all integers and plus is the addition operation. So let's ask the first question, is the closure property true? So if I take any two integers and if I add them, then the resultant element is always an integer. So for example, if I do minus 3 plus 7, then I get 4, which is also an integer. So if you take any two integers, you add them, the resultant element is always an. Second property is that of associativity, and this is something we know from the algebra of numbers, that if you take any two integers, and it does not matter whether you the order of operations that you do, the result would always be the same. So the commutativity is also true. Now let's ask the interesting question of whether there's an identity. So um, yeah, so what do I mean by identity? I want an element such that if I add it to any other number, I should get back the same number, and we know that that number is 0. So if I look at any number and I add 0 to it, I'll get back n. So 0 is the identity. And the fourth thing that we have is what is called inverse. That is, if you give me a number n, can I add it to another n prime so that I get 0, which is the identity. And we know that n prime, if you take n prime to be minus n, then then this is the inverse of n, and it is also an integer. So it does satisfy closure, associativity, identity, and inverse. It satisfies all the four properties, therefore it's a group. But what we additionally observe is the fifth property that we were mentioning, which is about commutativity. So we know that if you take any two numbers, any two integers, then n plus n prime is always same as n prime plus n. For example, 3 minus 7 is same as minus 7 plus 3. Okay, so right, so that means it does not matter what order you are performing the operation, the answer is going to be the same. So in this case, it so happens that it's also commutative, and hence it's not just a group, it's an abelian group. Okay. Now okay, let's look at the second example, which is n plus. Okay, so let's again ask the same questions. Closure. So first thing is that if you add any two natural numbers, you will get back a natural number. So closure is guaranteed. Again, associativity is guaranteed. This again follows from the property of numbers. Now the important question that we ask is identity, and assuming that the set of natural numbers that you have is 0, 1, 2, 3, and so on, 0 is contained in the set of natural numbers, therefore 0 is the identity, just like previous example. The fourth property that we want to understand is that of an inverse. So in the earlier case, for example, if I had 3 and I add minus 3 to it, then I get back the identity, and it was still in the set Z. But in this case, that's not the case. I cannot add a positive integer, I cannot add a positive natural number and expect to get me 0, because it can only increase the sum. So the inverse does not exist. So yeah, so therefore since this property is not true, it is not a group. Now let's look at the third example. So the third example is that you have the set of matrices. The set that I have is the set of matrices, so of dimension n cross n. Okay, So this is what the set will look like. So there's some n cross n with 1 0 0 0 0 1 0 1 0 and so on. It's an n cross n, and this is the set, which is yeah. Okay, and the operation that I'm doing on these matrices is let's say addition. So okay, so maybe I'll just do, okay, it's maybe, let's assume it's not a Boolean matrix, so the values could be 2 3, it could take values, the values in the matrix are integers. Okay, and now what we'll do is we will ask the questions again. Notice that the addition of matrices is a well defined operation. So first question that we'll ask is that of closure. So if I add two matrices, I get back another matrix C, which is again of n cross n dimensions. If you add n cross n plus n cross n. So okay, so that gives you yeah, so that gives you an n cross n dimension matrix, which is again in the set S that you have. So closure is guaranteed. Let's ask associativity, and this is something that we know from the property of matrices, that if you add two matrices and then add the third one to it, that's same as adding the other two and then summing it with a. So associativity is something that we already know. The next interesting question that we ask is there an identity? So third question is there an identity? So what you do is you take your all zero matrix. So A plus 0 would be same as A. That is, if I have some matrix here with some entries and I add it to the all zero matrix, then I get back the same original matrix and so on. So 0 is the all zero matrix is the identity matrix for the matrix multiplication, addition. And now the question that we ask is whether there's an inverse. So what I'll do is I'll look at the matrix and I'll simply multiply all the values with the minus 1. So if I want A plus A prime to be equal to all zero matrix, then A prime better be minus A. That is, you multiply the entire matrix with a minus 1. So for example, I have this matrix 1 2 0 1 2 4 minus 2 0. Okay, maybe I'll just take a smaller one, and 3 minus 3 1. So this is the matrix A I have. Now I multiply this with a minus 1. So what I get is minus 1 minus 2 0, minus 2 minus 4 2, minus 3 3 minus 1. And if I add them together, 1 and minus 1 cancel out, 2 and minus 2 cancel out. Essentially everything cancels out and I get back an all zero matrix, which is identity. So yeah, so what you do is that the inverse of the matrix is simply you multiply every entry of the matrix with the minus 1, and when you add them together you will get the zero matrix. So this is indeed a group, and like earlier we know it's a commutative group because A plus B in case of matrix is same as B plus A. So it's an abelian group. Okay, so now let's maybe just to flip the question slightly, let's change the operator of the matrix. So instead of doing addition of matrix, I'm going to do multiplication of matrices, which is well defined. So if you have n cross n and n cross n matrix, that is a well defined operation to do. So what do you think would happen? Is it still a group? Is it an abelian group, if at all it is a group, or is it not a group at all? So I'll change the matrix set, but the operation this time is a multiplication. Okay, so what we'll do is let's start with the same question again. So we'll ask the closure property, and like earlier, we know that if you multiply two matrices, you get back an n cross n matrix, and yeah, if you multiply two integers, you get back an integer. So this is indeed in the set S. So closure is guaranteed, associativity is guaranteed again uh, by the laws of multiplication, the properties of matrix multiplication. And the interesting thing is identity. So what is the identity of this set? So I want to multiply it with a matrix, with some matrix here, such that I get back the same thing. So we know that there's such a matrix is an identity matrix. So for example, I have 2 3 1 0 2 3 1 4 5, and I multiply it with this 1 0 0 0 1 0 1 0 0 1, then I get back the same matrix. So this identity matrix is essentially your identity matrix, where if you multiply any matrix with that, you get back the same matrix. So let's understand whether the inverse exists. That is there a matrix A prime, which if I multiply A with, I get back I. And we know from the properties of matrices that not all matrices are invertible. If there is an A prime such that you can multiply it with A and get back identity, those matrices are called invertible matrices. But if you do not have, which, yeah, so there are matrices that are non-invertible. Okay, so yeah, so that is what we have, and therefore this is not a group. And I'll just end this discussion with that. The fourth question is something that you can try out. It is also similar, very similar. So I'll leave it to you as an exercise. Now let's move to the next question, which is I'll read it out first. So you are given a group G and you have an operation star, and we have made 4 statements about it, and we want to tell which of the statements are true about the group and which are not. So the first statement says that if C is equal to A star B for some A, B in G, then A star C should also be in G. And the second statement says that there can be multiple identity elements in G, but there can only be a unique universe. The third statement says that if you multiply, this is basically the associativity property, where whether you multiply BC first and then with A, or you multiply AB first and then with C, it does not matter. And the fourth statement is that if you look at A star B star C, that should be same as C star B star A, which for every element ABC. So maybe take a pause for some time and think about which of these could be true, or yeah. So okay. So let's try to solve this. Let's take statement by statement which of these are true and which of these are not true. So let's understand statement 1. So this says that C is A star B for any AB, and now what happens to A star C? So notice that by closure property, since D is a group, by closure property C must be in the group first of all, and now since C is in the group and A is in the group, Then if you multiply them again, the resultant element, whatever it is, I'll call it X, this should also be in the group, and therefore A star C is in the group. So this follows from the closure property. So this is indeed true. So statement 1 is true. Now let's understand the statement 2, which says that you can have multiple identity elements, but there can be only a unique unique inverse. So notice that you cannot have, given a group, the identity, there is a unique identity element in a group G. Why is that? Because for example, suppose not, so there are two distinct E not equal to E prime, such that for all A in G, A dot E is equal to A dot E prime is equal to E is equal to E prime. Okay, so okay, maybe I'll write it step by step. And A dot E prime is also equal to E prime. So suppose this happens. Okay, now what we'll do is is equal to A dot. Okay, just give me a minute. Okay, so what I'll do is I'll multiply these with E prime. So this is same as E prime dot E, and since A dot E is E, okay, so okay, so E of E prime is same as E, and E prime of E is same as E prime, and E of E prime is same as E prime of E, which is same as E, which is same as E prime, which is a contradiction to the fact that E and E prime are the same element. So we just use the fact that E is identity for E prime and E prime is identity for E, and then we just equate it together to say that both are essentially the same elements. So this is not possible. In fact, you cannot have you cannot have two different identities, and same goes with the inverse. You cannot have two distinct inverses in the, so same thing goes for, so that already says that statement 2 is not true, but we'll just show that given a group G, for all A in G, there is a unique inverse of A. Okay, so how do we do that? Again, you assume this is not the case, then A dot A prime is E, and A dot A double prime is also E, and now you try to equate them. And what I'll do is I'll pre-multiply them, and I know that A dot A double prime is identity, because A double prime is also an inverse. So A prime dot E is same as A prime dot A is also identity, so E dot A double prime, and that gives you A prime is equal to A double prime, which is again a contradiction, so to the fact that these are distinct. Okay, So in the similar way, you can show that if I give you a group, the inverse of every element should be unique. So that already disproves the statement 2. The statement 3 is simply the associativity property, which we have already seen. So statement 3 is nothing but the associativity property, and this we know is definitely a property of a group. So the only thing that remains to see is the statement 4, which is that A star, C star, A star. Okay. So yeah. So this is something that this is something that depends on the commutative property of the group. If it's commutative, that is A star B is same as B star A, then you can say that this thing holds. But in the definition of the groups that we had only 4 properties: associativity, closure, identity, and inverse, and none of that imposes this structure. So you can very well have a group which does not satisfy this condition for all A, B, C, and therefore this is not a valid statement about general group. So the answer to this is statement 1 and 3, which is um, yeah which is option B. Okay, so if that is clear, I'll move on to the next question. So here you are given um, 3 groups which are given by the tables. These are called Cayley tables in the in the case of groups. So I'll just write it. It's not necessary to know, but I'm just letting you know that this is what is called a Cayley table. And how do you read it? It just says that A operated on A gives you the element A operated on B gives you B, and so on. So that's how you read the table. Like, typically, that's how you read the table. And the group is defined on 4 elements, or the set that is associated with it is A, B, C, D, and the operation that you have is how does the group operate is given by the table, the values in the table. And now you want to test whether which of these are groups and which of these are not groups. So how do you test that? You check for all the 4 properties, and whichever property is violated, if you find such a property, then it's not a group, and if it satisfies all the 4, it's a group. So maybe take some time, pause the video and take some time and try to solve this by yourself, and we will discuss the solution so in a short while. Okay, so let's try this step by step. Maybe I'll so first thing that we know is that it should satisfy the closure property, which is if I multiply any 2 elements, I should get an element within the set that I have. So notice that if I look at the entries in the table, these are all in the set, contained in the set ABCD. They do not go beyond that. So the closure property is guaranteed. Second thing is the associativity, which maybe we'll check on later on, because it's typically hard to check because there are a lot of conditions, but the easy ones maybe would be identity. So if it does not satisfy identity in the first place, then I will reject it then and there. So let's look at identity for the first group. So here notice that if I look at this element A, then if I multiply it with any other element, it gives me back the same element. So A with A gives me A with B gives me B, A with C gives me C, and A with D gives me D. And same thing happens in this column for A. So that means A is an identity element for this group. Let's look at the second group. Again, this A itself is an identity for the second group because it gives you the same element on multiplying them together. And same thing holds for the other one also. So identity holds for all of them. Now the third thing that we want to check, which is important, is what is called the inverse. And yeah, and okay, maybe before we get there, let's observe one claim that we know. So we from the previous discussions, we know that for any group there is a unique identity element. Okay, so let's look at what do we mean by that. So okay, so okay, so maybe let's start with the G3. So okay, and maybe I'll write the second property also. And for all A and G, there is a unique inverse. Okay, but if we look at G3 for example, then G3 has then G3 has two inverses because C dot A also gives you C, and okay, and C dot, okay, maybe I'll talk about G2 first. So if I look at G2, then C dot C also gives me A, and C dot D also gives me A. So notice that so notice that in this case C is the inverse of C, and here D is the inverse of C. So there are two inverses for C, which cannot be the case because of the theorem that we proved just now. So this G2 is not a group. Okay, and similarly let's look at G3. So what is the problem with G3 is so the problem with G3 is that there is no inverse for C. So for example, if I look at C, there is no element that I can multiply that will give me the identity element, which is A. So I multiply C with A, I get back C. I multiply C with B, I get back D. C with C gives me C, and C with D gives me D. So it does not give me the identity element A. And by the property of inverses, so for G3, inverse is violated. That is, there does not exist an element X in G such that C dot X is equal to A, as we can see from the table. So G3 is not a group, and therefore only G1 is a group. So the answer is A. Okay, so I hope that is clear. So if that's the case, then I'll move on to the next question, which is again about groups. Okay, so let's define. So far the sets and operations that we were defining were with numbers. So just for a change, let's define the set to be um, the set to be the set of all words in English alphabet which is infinite. So, and it need not be meaningful. Those are just any words that I mean, there's just a set of words that don't even make sense. So the set of words is the set of words is given by W. So set W is a word over A to Z, A to Z, star, union E. Okay, and epsilon just denotes the empty string. And what is the operation that we have? The operation is simply the concatenation operation. So for example, if I say APP concatenated with LE, then that gives me the word apple, and so on. So the question that we are asking now is, does the set W over this operation of concatenation, does this define a group? That is, does it satisfy the 4 properties that we have mentioned? Okay, so let's try to solve this. So first thing is the closure property, and notice that if I take any word here and I concatenate it with any word here, that gives me back another word which is a valid word over English alphabet. So the closure property is trivially holds. In fact, even if I take okay, and maybe I'll get there later. And associativity is that I take this word APP and another word and then another word, and okay, and what I do is I first concatenate these two, and then I concatenate the result with this, or I first concatenate these two and then I concatenate it with CE. So this is what you have. Then I get back the same thing, which is apple juice. So it does not matter what order in which I am doing it, whether I am doing this first and then this, or this first and then this, I am going to end up with the same string. So this is indeed associativity. This follows from the property of the strings. The interesting question is identity. So I want an element which I know for every word W, if I multiply it with E, then I'm gonna get back the same word. So this for us is the empty string, which is epsilon. So if I look at apple and I concatenate it with epsilon, I get back apple, and this happens for every word. So therefore there is indeed an identity, and the identity is epsilon, which is again unique. And the fourth property that we want to see is what is called the inverse. And now the thing is, that I want to, so for example, I take this word, I want to multiply it with another word so that I get back epsilon, and that is not something that you can do with concatenation, because no matter what I write here, it's only going to append, it's only going to increase the length of the string. So there is no inverse for any word. So therefore there is no, this is not a group. Okay, so if that is clear, I'll move on to the next question. Okay, so we will define what is called a subgroup. Maybe we'll not do all the examples, but we'll try to do some of them. So I need to define what is called a subgroup of a group. So let's say G is a group over set S, and operation is say star. Then I say that H is a subgroup of G. This is denoted by H is a subgroup of G if, maybe I'll just call this G star, if H over the same operation is a group. What do I mean by that? That just means it satisfies all the four properties: closure, associative, identity, and inverse. So if this happens, then I say that it is a subgroup. And let's say I have Z plus, then what I do is I okay, so this is something that we did earlier, and we know that this is a group. This is what is given. Now I want to check if Z is a subgroup of G. So indeed Z plus is a subgroup of G, which is a group, which indeed is a group. So this is a valid subgroup. Second one is all the sets which are at least 0. And in this case, what happens is I have the closure property. Because I add two integers, I get back the integer. I have the associativity property that just follows from the property of the numbers. I have the identity, which is 0. That is, I add anything to the I add anything and I get back the same element, but the inverse does not hold. For example, 2 does not have an inverse. I cannot add anything here and get back a 0 because I only have the set of positive numbers. In fact, this is the same as the previous example that we did in the previous question, where you had natural numbers and operation was plus. So we saw earlier that this is not a group, and therefore this is not a subgroup. Okay, so I'll not get into this further because I think this is this conveys what we want to say. All we're saying is you just check if this forms a group over the same operation. So this is something that is important. You don't want to change the operation. I don't want to say Z multiplication over this is a group. You have to necessarily take this same operator and check if it's a group by checking all the all the properties. If it does satisfy, then it's a subgroup. If it does not, it's. So take this to C and D as homework and try to attempt. Those are both interesting questions. So I'll move on to the next, the last question for today, which is that you have a group which has 78 elements in it, and the operation is something that I'm not defining, which it does not even matter for the question. So you want to find out what is the largest possible subgroup, proper subgroup of G that it can have. So what do I mean by proper? So earlier when we saw this example of Z is not a proper subgroup because you have taken all the elements of Z and put it into this. So it's the definition of proper is same as that you have for sets, whereas this is proper subset because there are elements in Z which are not there in the set that you have. So essentially I want to take a proper subset of the group that is given and with the same operation, and ask what is the largest possible subgroup that I can have. So the answer to this strange question is lies in the simple application of Lagrange's theorem. So Lagrange's theorem says that if I look at a G, which is a group, and I look at the cardinality of G, and I divide it with the cardinality of any subgroup H, so H is a subgroup of G, then this is okay, then I mean essentially this is an integer, that is size of H divides size of G. That's what we mean. So notice that I am not allowed to have 78 size of H as 78 because we said we want a proper subgroup. So what is the next largest number that you can have? You can have it as 78, that is size of G by size of H is equal to 2, that is size of H is 78 divided by 2, which is 39. So 39 is the largest possible group that you can have. We are not saying that there definitely is a subgroup of this size, but we are saying if there is a subgroup, the largest size could be 39. So that is a nice application of Lagrange's theorem. Okay, so I'll end the lecture with that. So what we saw today is we saw chromatic polynomials. We saw how to use polynomials to answer advanced combinatorial questions. Then we saw the groups and what are the properties of the groups and some interesting theorems on the groups. So we'll not dive into this topic a lot, but it is a research area on its own, and it's very it's very useful. So yeah, so what we'll do is we will meet yeah, next we will meet on the coming Monday, the same. Okay, I'll maybe share it and write it again. um, okay, so next we will meet on Monday, the upcoming Monday, from 6 p.m. to 8 p.m. the same time. You will uh, you will get an you will get an invite for the same. So I'll maybe I'll end the lecture with that. So thank you.